Hubble reveals Abell 209 as a monumental concentration of galaxies, bound together not just by visible matter, but by a vast gravitational field dominated by the unseen. Located approximately 1.3 billion light-years from Earth, this cluster represents one of the most massive structures ever observed, a gravitational citadel sculpted by dark matter and ancient collisions. Its core glows with the combined light of hundreds of galaxies, many of which have long ceased star formation, fossil remnants of a more turbulent cosmic past. What makes Abell 209 particularly compelling is not just its size, but its intricate gravitational influence. Acting as a natural cosmic lens, it distorts and magnifies the light from galaxies lying far beyond, revealing otherwise invisible regions of the distant universe. These distortions, luminous arcs, smeared spirals, and magnified cores, are not mere optical curiosities. They are direct evidence of the immense mass hiding within, far surpassing the sum of what we can see. Astronomers use this lensing effect to map the distribution of dark matter, tracing its ghostly presence through spacetime. The space between galaxies within Abell 209 is not empty. It is filled with a superheated plasma, reaching tens of millions of degrees, detectable only in X-rays. This intergalactic medium tells a story of high-speed collisions and mergers, galaxies pulled and torn by tidal forces, slowly dissolving into the cluster's gravitational well. This gas, stripped from galaxies as they plunge into the core, becomes part of a diffuse halo, glowing faintly as it cools across cosmic time. Hubble's view pierces this distant realm with extraordinary clarity. The instrument's precision has allowed scientists to resolve even the faintest members of the cluster, dwarf galaxies orbiting their massive companions, relics of a time when the universe was still assembling its grandest structures. These small satellites may hold clues to the early conditions of galaxy formation, fossil witnesses to a younger cosmos. Abell 209's internal dynamics reveal a system in motion, not static or settled. Its galaxies travel at incredible velocities, their orbits shaped by a central mass so vast that even the fastest-moving members remain gravitationally bound. This motion contributes to the overall heating of the cluster, stirring the plasma and occasionally triggering shock fronts, echoes of long-past galactic collisions that ripple through the medium like seismic waves. Gravitational lensing maps of Abell 209 have become key tools in testing the limits of general relativity. The deviations between visible and invisible mass distributions offer insights into the large-scale structure of spacetime. Some researchers now explore whether the arrangement of galaxies and dark matter in such clusters follows fractal-like patterns, governed not by chaos, but by hidden mathematical order. Others speculate about unknown forces or particles that could subtly influence these colossal systems over billions of years. With every new observation, Abell 209 deepens the mystery. Its structure, luminous and obscure, challenges our understanding of cosmic evolution. It is not merely a collection of galaxies, it is a system shaped by forces we cannot yet fully define, an experiment billions of years in the making, unfolding in the fabric of the observable universe. The study of Abell 209 has become a focal point for understanding the assembly and evolution of large-scale cosmic structures. Observations with the Hubble Space Telescope, combined with data from Chandra, XMM Newton, and ground-based facilities such as VLT and Subaru, have allowed astrophysicists to construct detailed multi-wavelength portraits of this cluster, revealing its complex internal structure and mass distribution. Hubble's optical imaging exposes hundreds of galaxies tightly packed in a region only a few million light-years across, while X-ray data trace the diffuse hot gas that dominates the baryonic content of the intracluster medium. Spectroscopic surveys of Abell 209 have measured the redshifts and velocities of its member galaxies with high precision. These dynamical studies show a velocity dispersion exceeding 1,000 km per second, confirming the cluster's deep gravitational potential well and suggesting ongoing mergers between subclusters. Several filaments of galaxies extend outward from the cluster core, indicating that Abell 209 is still accreting material along the cosmic web, in line with the lambda CDM, lambda cold dark matter, cosmological model. Weak gravitational lensing analyses provide one of the most powerful probes of the dark matter distribution in Abell 209. By measuring the subtle distortions in the shapes of background galaxies, scientists have reconstructed a mass map of the cluster, revealing that the majority of its mass resides in extended halos of dark matter, not cospatial with the visible baryonic matter. This separation between mass and light is consistent with findings in other massive clusters, such as the Bullet cluster, and further supports the non-baryonic nature of dark matter. Studies using Sunyaev-Zeldovich effect measurements, particularly from the South Pole Telescope, SPT, and the Atacama Cosmology Telescope, ACT, have provided independent estimates of the pressure and density of the intracluster gas in Abell 209. These data, when combined with X-ray observations, allow for hydrostatic equilibrium modeling, yielding total mass estimates that align closely with lensing-derived masses, though slight discrepancies suggest additional non-thermal pressure support, possibly from turbulence or bulk motions within the gas. Infrared imaging with Spitzer and Herschel has revealed a population of dusty, star-forming galaxies within Abell 209's outskirts, many of which are undergoing ram pressure stripping as they fall into the denser cluster environment. These environmental effects have been studied in detail, showing that galaxies in the central region exhibit quenched star formation, truncated gas disks, and morphological transformation from spirals into lenticular or elliptical types, a hallmark of cluster-driven evolution. Deep ultraviolet imaging and integral field spectroscopy have uncovered post-starburst signatures in a subset of galaxies, indicating that rapid quenching events occurred within the last 1 to 2 billion years. These signatures are often found in galaxies undergoing interactions or experiencing tidal forces within the cluster's potential, supporting models of transformation via harassment, starvation, and mergers. Simulations using cosmological hydrodynamic codes such as Illustris TNG and Eagle have been compared with the observed structure of Abell 209. The simulations reproduce the mass, concentration relationships and galaxy population statistics seen in the data, but also highlight limitations in current feedback prescriptions, particularly in modeling the distribution and entropy of intracluster gas at large radii. Some studies propose modifications to the AGN feedback models or include cosmic ray transport and magnetic fields to better align theoretical predictions with observations. Abell 209 has also served as a laboratory for testing alternative theories of gravity. Modified Newtonian dynamics, MOND, and scalar, tensor gravity models have been applied to the cluster's lensing and velocity dispersion data. While dark matter models remain consistent with the majority of observations, alternative gravity scenarios attempt to explain the gravitational potential without invoking exotic matter. However, the strong lensing arcs observed by Hubble, particularly near the core, pose challenges for MOND-based interpretations without invoking additional unseen mass. Chemical enrichment studies of the hot intracluster medium show enhanced abundances of heavy elements such as iron and silicon, implying enrichment from multiple generations of supernovae, both type Ia and core collapse. These metals were likely expelled from galaxies through galactic winds and AGN activity over billions of years. By comparing the metallicity gradients and alpha element ratios with those in other clusters, researchers gain insight into the star formation history of Abell 209's progenitor galaxies and the efficiency of feedback mechanisms. The orientation and ellipticity of Abell 209's mass distribution have also been analyzed to study large-scale anisotropies in the cosmic web. The alignment of galaxy major axes and filaments connected to the cluster core reveals evidence for a preferred infall direction, consistent with large-scale tidal torque theory. This provides further support for the hierarchical structure formation scenario, in which massive clusters like Abell 209 grow via anisotropic accretion of galaxies and groups along filaments. Radio observations, though limited in this specific cluster, have hinted at diffuse synchrotron emission possibly associated with a low-luminosity radio halo or relic. These features, if confirmed with deeper observations from instruments like LOFR or SKA, would indicate the presence of relativistic particles and magnetic fields permeating the intracluster medium, another layer of complexity in the physical processes governing massive clusters. Further investigations of Abell 209 have incorporated statistical analyses of galaxy morphology-density relations within the cluster, revealing a clear correlation between local environment and structural transformation. In the dense core regions, the fraction of early-type galaxies, ellipticals and lenticulars, approaches 80%, while in the outskirts, a more diverse population of late-type, gas-rich spirals remains. This gradient aligns with the classical morphology-density relation first established by Dressler, reinforcing the idea that the dense cluster environment plays a dominant role in halting star formation and reshaping galaxies. Kinematic data from integral field spectrographs such as MUSE on the VLT have allowed astronomers to trace the internal rotation and dispersion profiles of individual galaxies within Abell 209. These data provide constraints on the dynamical histories of cluster members, revealing whether they have undergone recent mergers, tidal stirring, or stripping. Some galaxies show truncated rotation curves or disturbed kinematics indicative of harassment by repeated high-speed encounters in the cluster's crowded environment. The study of globular cluster systems in Abell 209 has added another layer of information. Deep Hubble photometry has detected extended halos of globular clusters surrounding the central brightest cluster galaxy, BCG, consistent with hierarchical growth through mergers. The spatial distribution and metallicity bimodality of these globular clusters also offer a fossil record of the cluster's assembly history, pointing to early epochs of rapid mass accumulation. Intriguingly, a weak but statistically significant misalignment has been observed between the peak of the X-ray emission, the lensing mass centroid, and the BCG in Abell 209. This offset suggests that the cluster is dynamically young and may still be in the process of relaxation after a major merger event. Such offsets are used as indicators of recent or ongoing interaction between subclusters, providing insights into the dynamical timescales of cluster relaxation and the interplay between baryonic and dark matter components. Polarization studies and Faraday rotation measurements from background radio sources passing through Abell 209 have been proposed as a means to probe intracluster magnetic fields. While current constraints remain loose, future deep polarization surveys with SKA and INVLA could detect tangled magnetic fields on kiloparsec scales, helping to explain the origin of magnetism in the cosmic web and its effect on thermal conduction, particle acceleration, and shock propagation in the cluster plasma. Furthermore, the gravitational lensing arcs in Abell 209 have been used as background candles to estimate cosmological parameters. By modeling multiple image systems and applying time-delay lensing methods, researchers can place constraints on the Hubble constant, h, and the geometry of the universe. While the uncertainties are still large compared to local measurements, clusters like Abell 209 add valuable independent datasets to the growing body of lensing-based cosmology. From a theoretical perspective, semi-analytic models, SAMs, and machine learning techniques have been applied to reproduce the observed color, magnitude distributions, luminosity functions, and satellite abundances in Abell 209. These approaches attempt to encapsulate the complex baryonic physics, cooling, feedback, environmental quenching, into efficient algorithms that can be applied across cosmological volumes. The ability of these models to reproduce Abell 209's observed properties is a key benchmark for the validity of galaxy formation theory in dense environments. On the cosmological frontier, Abell 209 contributes to constraints on the mass function of galaxy clusters, one of the most sensitive indicators of the underlying cosmological model and the growth of structure. Its mass, redshift, and internal structure help refine models of structure formation, test dark energy equations of state, and probe the mass-richness relation used in large optical surveys like DES and LSST. Additionally, simulations of particle trajectories and shock propagation in clusters like Abell 209 are used to model the production of high-energy cosmic rays and secondary neutrinos. These processes, though not yet directly observed in this particular cluster, are part of a broader effort to understand galaxy clusters as astrophysical laboratories for particle physics, where dark matter annihilation signals or axion-like particles might one day be detectable. All these observations and theoretical efforts make Abell 209 more than a distant collection of galaxies. It becomes a dynamic laboratory, an ancient structure still in evolution, offering a window into processes that shape the visible and invisible cosmos alike. Abell 209 continues to serve as a cornerstone in the study of hierarchical structure formation and the nonlinear evolution of cosmic matter. As one of the more massive and dynamically active clusters at intermediate redshift, it sits at a crucial juncture in cosmic time, roughly halfway between the Big Bang and the present era, offering a snapshot of the universe during its large-scale consolidation phase. Detailed comparisons with high redshift protoclusters and low redshift relaxed systems position Abell 209 as a transitional object, bridging the gap between violent assembly and gravitational equilibrium. One particularly compelling avenue of research centers on the entropy profiles of the intracluster medium, ICM. Entropy, a measure of the thermal history of the gas, increases as clusters evolve through mergers, shocks, and feedback. Observations with XMM Newton and Suzaku have been used to reconstruct the radial entropy distribution in Abell 209, revealing a flattening at large radii that deviates from simple gravitational heating models. This entropy suppression suggests that non-gravitational processes, such as AGN feedback, turbulence, or cosmic ray pressure, have significantly modified the thermal structure of the gas, injecting additional complexity into energy transport mechanisms at cluster scales. The mass-concentration relation, which describes how dark matter is distributed within a halo as a function of its mass and redshift, has also been studied in Abell 209 using parametric fits to lensing and X-ray data. Interestingly, this cluster exhibits a relatively high concentration parameter for its mass, which may indicate an early formation epoch or the influence of ongoing mergers that deepen the potential well. Such deviations are important because they can be used to test modifications of cold dark matter, CDM, or the presence of self-interacting dark matter, SIDM, which predicts different core structures and heat transfer properties within clusters. Abell 209's brightest cluster galaxy, BCG, has been the subject of intensive stellar population analysis. Deep spectroscopy with instruments such as Keck/DIMOS and VLT/X-Shooter has shown that its stellar population is predominantly old, with metallicities approaching solar values and little evidence for recent star formation. However, faint shells and tidal features surrounding the BCG, revealed in high-contrast Hubble imaging, indicate past dry mergers, accretion events involving little gas but significant stellar mass. These features suggest that the BCG continues to grow through minor mergers, in line with hierarchical assembly scenarios. The role of preprocessing, the transformation of galaxies in group environments before they enter the main cluster, is also evident in Abell 209. Substructure analyses using galaxy redshifts and X-ray temperature maps have identified infalling groups along filaments. Galaxies in these groups already show signs of morphological transformation and quenched star formation, implying that environmental quenching begins well before galaxies reach the cluster core. This two-stage transformation, preprocessing followed by cluster-specific effects, has become a central theme in modern galaxy evolution theory. In terms of cosmic web connectivity, Abell 209 is believed to reside at the intersection of several large-scale filaments, as indicated by galaxy density contours and large-volume simulations. These filamentary structures serve as conduits for matter inflow, guiding gas, galaxies, and even smaller clusters into the growing central potential. Observing these filaments is challenging, but recent developments in low-surface brightness imaging and weak lensing tomography offer promising avenues for direct detection. Mapping the kinematics and thermodynamics of these filaments may ultimately provide insight into the mechanisms that fuel cluster growth and heat the ICM. Another emerging frontier involves the application of machine learning algorithms to analyze the vast, multi-wavelength datasets associated with clusters like Abell 209. Convolutional neural networks, CNNs, have been trained to identify cluster substructure, classify galaxy morphology, and even predict mass distributions from imaging data alone. When applied to Hubble and Subaru images of Abell 209, these models have successfully isolated features such as lensing arcs, intracluster light halos, and diffuse tidal streams, demonstrating the power of AI-assisted astronomy in extracting subtle patterns from complex, high-dimensional datasets. Additionally, intracluster light, ICL, the diffuse glow emitted by stars that are no longer gravitationally bound to any single galaxy, has been mapped in detail within Abell 209. This ICL forms from the accumulation of stripped stars over time and serves as a luminous tracer of past dynamical interactions. The spatial extent, color gradients, and stellar populations of the ICL provide valuable information about the cluster's merger history and the efficiency of tidal stripping in different environments. In Abell 209, the ICL accounts for a significant fraction of the total stellar mass, suggesting a long history of galactic cannibalism and disruption. In the larger cosmological context, Abell 209 contributes to the calibration of scaling relations, empirical correlations between observable properties, like X-ray temperature, optical richness, and SC flux, and total mass. These scaling relations are essential for turning cluster catalogs from surveys like Eurozeta, Euclid, and LSST into cosmological probes. Accurate mass measurements of clusters like Abell 209, grounded in lensing and X-ray hydrostatics, help reduce systematics in dark energy experiments and improve constraints on structure growth parameters such as sigma 8 and omega. Even time-domain astronomy is beginning to play a role in cluster studies. Monitoring transient events such as supernovae, active galactic nuclei, AGN, variability, and possible fast radio bursts, FRBs, within and around Abell 209 opens new possibilities for probing the baryonic content and ionization state of the intracluster medium. Although still speculative, the detection of a lensed FRB through Abell 209 could provide exquisite constraints on both the cluster's mass distribution and the properties of the intervening plasma. The scientific exploitation of Abell 209 has also led to progress in understanding the baryon budget problem in clusters. Observations indicate that the total baryonic mass, from stars, cold gas, and hot plasma, in Abell 209 is slightly below the cosmic baryon fraction predicted by the standard lambda-CDM model. This discrepancy suggests that a fraction of the baryons may be in forms difficult to detect, such as warm-hot intergalactic medium, WIM, turbulent gas that escapes X-ray detection, or even low-mass, low-luminosity galaxies that fall below observational thresholds. Reconciling observed baryonic content with theoretical expectations remains an active area of research, and clusters like Abell 209 are prime testbeds for quantifying this deficit. Phase space diagrams, which plot galaxy velocity versus radial distance from the cluster center, have been constructed for Abell 209 using high-resolution spectroscopic data. These diagrams reveal the dynamical state of galaxies, those recently accreted, those in first infall, and those that have been virialized. The characteristic trumpet-shaped caustic pattern seen in Abell 209 allows for an alternative, non-parametric estimate of its mass profile, independent of assumptions about dynamical equilibrium. The sharp boundaries of these caustics help define the virial radius and map the extent of the cluster's gravitational influence in phase space. In terms of stellar mass functions, studies have shown that Abell 209 has a bottom-heavy galaxy population in its core, with a steep faint end slope. This suggests enhanced survival or accumulation of low-mass galaxies in the cluster center, possibly due to dynamical friction, tidal compression, or suppression of feedback mechanisms in the high-pressure environment. In contrast, the outskirts display a flatter mass function, indicative of field-like populations and ongoing infall. These radial trends inform semi-analytical models of hierarchical assembly and environmental quenching. Abell 209 also contributes to the exploration of galaxy lensing within clusters. In addition to the large-scale cluster lensing signal, individual massive galaxies within the cluster act as secondary lenses, producing smaller-scale distortions in the images of background galaxies. By analyzing the combined shear signal, researchers can isolate the mass of individual halos, including dark matter subhalos, and study how they are stripped or truncated as galaxies move through the cluster environment. The degree of subhalo truncation provides empirical constraints on the physics of tidal stripping, halo occupation distribution, HOD, and substructure evolution. Recent advances in spectral energy distribution, SED, fitting using broadband data from UV to IR have enabled precise modeling of stellar populations in Abell 209. These models allow estimates of stellar ages, metallicities, and dust contents across the cluster population. For example, passive galaxies in the core exhibit older stellar ages, greater than 10 gyre, and high alpha/Fe ratios, implying short and intense star formation histories. Meanwhile, galaxies in transition zones between the core and infall regions often show signs of rejuvenation, with modest bursts of star formation triggered by tidal interactions or gas compression. The cluster's intracluster supernova rate is another observable tied to its dynamical state and star formation history. Ongoing monitoring with space-based telescopes aims to detect Type Ia supernovae not associated with any host galaxy, believed to originate from the diffuse stellar population or from stripped systems. These hostless supernovae trace the ICL and provide constraints on the formation and metallicity of the intracluster stellar population, as well as on the delay time distribution of Type Ia progenitors. Abell 209 has been included in large compilations for cosmic chronometer studies, where passive galaxies are used as standard clocks to measure the expansion rate of the universe as a function of redshift. By precisely dating the stellar populations of early-type galaxies via spectral indices, e.g., D4000 break, scientists can determine differential age evolution and thus place independent constraints on h, z, the Hubble parameter at redshift z 0.2 to 0.3. Clusters like Abell 209, with well-characterized passive members, are ideal environments for minimizing uncertainties in this method. From a thermodynamic standpoint, pressure and entropy maps derived from X-ray and SC observations allow for reconstruction of the virialization state of the cluster. In Abell 209, these maps show irregularities and asymmetries, particularly in the southeast quadrant, suggesting the presence of residual bulk motions or merger-induced turbulence. Such turbulence could contribute to non-thermal pressure support, biasing hydrostatic mass estimates low compared to lensing-derived masses. These discrepancies are critical for cluster cosmology, as they affect the calibration of mass, observable scaling relations. The evolution of central metallicity peaks in Abell 209's ICM offers insights into the efficiency and timing of chemical enrichment processes. Observations indicate that the iron abundance drops outside the core but maintains a broad peak rather than a sharp one, suggesting mixing of metals via AGN outflows, sloshing, or past merger activity. The ratio of alpha elements, like O, Na, Mg, to Fe further constrains the relative contribution of core collapse versus Type Ia supernovae, providing a fossil record of star formation in cluster progenitors. Comparisons between Abell 209 and simulated clusters in hydrodynamical cosmological runs, such as Magneticum Pathfinder or the 300 project, have validated some observational trends but also highlighted tensions. For example, simulated clusters often exhibit too much cool core preservation or insufficient turbulence, prompting refinements in AGN feedback prescriptions, gas clumping treatment, and the inclusion of anisotropic thermal conduction or magnetohydrodynamic effects. Finally, Abell 209 is now part of upcoming multi-wavelength synergy campaigns that aim to observe clusters across the electromagnetic spectrum, from Erosate's X-rays to Euclid's near-infrared weak lensing, and SKA's low-frequency radio mapping. These projects will refine dark matter maps, trace cosmic magnetism, detect previously unseen filaments, and constrain the assembly of structure on gigaparsec scales. Pushing deeper into the frontier of high-energy and multi-messenger astrophysics, Abell 209 also emerges as a potential candidate for indirect studies related to neutrino physics and dark sector interactions. While not yet directly observed, massive clusters like Abell 209 are expected to host relic neutrino populations that influence their large-scale dynamics subtly. Cosmological simulations incorporating massive neutrinos predict a slight suppression in small-scale power, which in turn affects the growth rate of clusters and the shape of their mass function. Accurate mass measurements of systems like Abell 209, when compared across redshifts, help constrain the sum of neutrino masses, sigma mu, a key parameter that links cosmology with particle physics. The presence of non-thermal phenomena, such as radio halos, mini-halos, or relics, is another area of growing interest. Though Abell 209's diffuse radio emission is faint, sensitive instruments like LOFR and UGMRT have detected low-frequency components consistent with a weak central radio halo. Such halos are thought to originate from synchrotron radiation of relativistic electrons accelerated by turbulent motions and magnetic fields in the ICM. Their existence is deeply tied to cluster merger histories and the nature of cosmic magnetism. The detection of polarized structures and spectral steepening within the halo of Abell 209 provides evidence for aging electron populations and potential reacceleration events, driven by shocks or magnetohydrodynamic turbulence. These magnetic fields, on the order of a few microgauss, influence everything from thermal conduction to particle diffusion and AGN feedback. Faraday rotation studies through background quasars and lensed radio galaxies offer one of the few observational probes of these invisible structures. While the current signal from Abell 209 remains marginal, stacking analyses of similar clusters reveal a statistical imprint of coherent magnetic domains extending over hundreds of kiloparsecs. Understanding their origin, primordial seeding, galactic outflows, or dynamos, is a major unsolved problem, and clusters like Abell 209 serve as natural cosmic laboratories for constraining field amplification scenarios. The potential detection of gravitational waves from compact binary mergers within clusters is an emerging possibility. While the rate of such events in clusters like Abell 209 is expected to be low, the dense galactic environment facilitates interactions that can lead to black hole or neutron star mergers, particularly via dynamical capture in globular clusters or galactic nuclei. Future space-based detectors like LISA will be capable of detecting low-frequency gravitational waves from supermassive black hole binaries in merging brightest cluster galaxies, BCGs, which are expected to form in the hierarchical growth of clusters like Abell 209. The eventual detection of such a signal, temporally coincident with electromagnetic signatures from BCGs or AGN, would mark the onset of cluster-scale gravitational wave cosmology. A different and equally fascinating area of exploration is the entropy-metallicity connection in the ICM. Recent work suggests that entropy and metallicity are correlated not only spatially but also dynamically. In Abell 209, outer regions with lower entropy show subsolar metallicities, whereas the core has higher entropy and more enriched gas. This challenges simple models of hierarchical enrichment and suggests a more nuanced picture in which AGN-driven outflows redistribute metals preferentially along low-density channels, while mergers stir the gas and flatten gradients. These patterns are being tested against cosmological magnetohydrodynamic simulations incorporating metal diffusion and anisotropic transport. Another advanced technique applied to Abell 209 is kinematic lensing, a method that combines lensing distortions with galaxy velocity fields to reconstruct the full 3D shape of the gravitational potential. While still in its early stages, this approach can, in principle, detect deviations from isotropy or symmetry in dark matter halos and may even test for signs of scalar fields or fifth forces at megaparsec scales. Abell 209, with its wealth of lensing features and well-measured redshift space distortions, provides a promising target for pioneering this kind of gravitational tomography. The cluster also plays a role in testing modified gravity theories such as F-bar-Tevis, or emergent gravity models. These alternatives to general relativity predict different scaling behaviors in the mass-velocity dispersion and mass-concentration relations. By comparing lensing-based mass estimates with those derived from dynamical or hydrostatic equilibrium, researchers have attempted to identify residuals or tensions that might hint at non-Einsteinian behavior. Though general relativity remains consistent with current data, the growing precision of cluster observables, particularly in dynamically unrelaxed systems like Abell 209, may expose subtle departures from standard gravitational theory. The use of principal component analysis, PCA, and nonlinear dimensionality reduction techniques on multiband photometric and spectroscopic data from Abell 209 has allowed for a more refined classification of its galaxy population. These data-driven methods, often paired with unsupervised learning algorithms, identify clusters of galaxies and feature space corresponding to evolutionary pathways, ranging from quenched ellipticals to transitioning lenticulars to dusty star-forming spirals. These classifications are then mapped back into real space and projected onto environmental gradients, revealing how the local density, ICM pressure, and cluster-centric distance drive galaxy transformation. Even in the realm of cosmic topology, Abell 209 has been involved in the construction of topological persistence diagrams, tools from computational geometry used to quantify the connectedness and void structure of matter distribution. These diagrams, when applied to galaxy distributions within and around the cluster, allow for the classification of features such as filaments, walls, and nodes in a mathematically robust way, independent of scale. Such approaches bridge the gap between large-scale structure and high-dimensional data science, and Abell 209 acts as a real-world case study in this cutting-edge framework. Diving further into the theoretical extremes, Abell 209 becomes a testbed for the intersection of quantum gravity, information theory, and macroscopic structure formation. While the cluster itself resides firmly in the classical regime, its immense gravitational potential, lensing power, and entropy content allow researchers to probe the boundaries of what we understand about gravitating systems in the high-mass, low-curvature limit of spacetime. One fascinating direction involves applying the Bekenstein-Hawking entropy formalism, originally developed for black holes, to large-scale structures such as galaxy clusters. In this analogy, the entropy of Abell 209 can be related not only to the thermodynamic entropy of its hot intracluster medium, ICM, but also to its gravitational entropy, a measure of how clumped and structured the matter distribution has become over cosmic time. In such treatments, entropy is not merely a function of temperature and particle number, but a manifestation of curvature and inhomogeneity in the underlying geometry of spacetime. Estimates of gravitational entropy, based on Weyl curvature tensors or Penrose's hypothesis of gravitational degrees of freedom, suggest that systems like Abell 209 represent some of the highest entropy configurations in the visible universe, short of black holes themselves. This prompts a broader question: is the formation of clusters like Abell 209 a statistical necessity of entropy maximization? If so, then the entire cosmic web might be viewed as an emergent thermodynamic structure driven by the statistical behavior of spacetime geometry itself. Closely tied to this is the concept of entropic gravity, pioneered by Verland, in which gravity is not a fundamental force but an emergent phenomenon arising from the entropic gradient of microscopic information. Clusters such as Abell 209, with their massive, extended dark matter halos and detailed lensing maps, offer a rare empirical playground to compare predictions of entropic gravity models against general relativity. While observational uncertainties still dominate, preliminary efforts have shown that deviations in radial acceleration curves or galaxy orbital behavior within such clusters may one day serve to falsify or support emergent gravity frameworks. In parallel, recent developments in holographic cosmology have inspired a new class of theoretical models in which the dynamics of a three-dimensional cluster like Abell 209 are encoded on a two-dimensional boundary or screen, conceptually similar to the AD/CFT correspondence in string theory. While not directly observable, this perspective allows for reinterpretation of gravitational lensing, thermodynamic scaling relations, and cluster entropy as projections of underlying quantum degrees of freedom, potentially opening a new path toward reconciling gravity with quantum mechanics. Abell 209's lensing features themselves have been studied under these speculative regimes. Quantum gravitational lensing, though not detectable at current resolution, posits that spacetime fluctuations at the Planck scale could, in principle, cause small deviations in the paths of photons traveling through massive cluster potentials. These fluctuations would manifest as phase decoherence or photon time delay noise, which over gigaparsec scales could introduce subtle lensing anomalies. While Hubble and JWST are not sensitive enough to detect such effects, next-generation interferometric missions may eventually be able to probe this quantum noise in strong lensing arcs around clusters like Abell 209. In the realm of dark energy, cluster coupling, some models suggest that dark energy is not a smooth, background scalar field but may exhibit local fluctuations or interactions near massive gravitational wells. In Abell 209, this raises the possibility that dark energy's effective density or pressure could vary subtly across the cluster's extent, modifying internal dynamics or contributing to non-standard potential gradients. Precision mapping of galaxy velocity dispersions, potential offsets between baryonic and dark mass, or anisotropies in X-ray isophotes may one day offer constraints on these exotic scenarios. Moreover, axion-like particles, hypothetical low-mass fields predicted in extensions of the Standard Model, could play a dual role in Abell 209, as a component of dark matter and as a mediating field influencing photon propagation. Clusters serve as potential converters for axion-photon mixing under strong magnetic fields, which could lead to spectral irregularities in the X-ray or gamma-ray emissions. While no such signature has been observed yet in Abell 209, its deep potential well and probable turbulent magnetized ICM make it a suitable target for axion searches using upcoming high-energy telescopes such as Athena or EXTP. On the data science frontier, there is growing interest in constructing simulated universes, self-consistent n-body and hydrodynamic simulations seeded with machine-generated initial conditions, to directly compare systems like Abell 209 to synthetic analogs. Generative models, such as GANs and diffusion-based frameworks, are being trained on real Hubble imaging to produce mock clusters with similar morphologies, filamentary connections, and lensing structures. These tools not only aid in interpretation but also allow scientists to explore the probability landscape of Abell 209-like structures under different cosmological models. Abell 209's position in cosmic time, redshift z is almost equal to 0.2, also enables critical constraints on the evolution of the matter-power spectrum. Large-scale measurements of galaxy clustering, lensing shear fields, and ICM thermal history all feed into constraints on parameters such as the growth rate of cosmic structure, f sigma 8, the running of the spectral index, and even possible departures from Gaussian initial conditions. The internal substructure, filament connectivity, and radial profiles of Abell 209 collectively act as fossil signatures of the primordial perturbations from which it formed, providing a high-resolution record of structure formation over the last 9 to 10 billion years. In totality, Abell 209 stands not merely as an astrophysical object of observational beauty, but as a multi-scale, multi-physics arena, spanning gravitational lensing, plasma astrophysics, dark matter dynamics, cosmic magnetism, galaxy evolution, entropy, and quantum cosmology. It is one of the rare cosmic structures where virtually every frontier of modern physics converges into observable form, waiting to be deciphered. Extending into infrared astronomy, observations of Abell 209 using instruments such as Spitzer and Herschel have provided vital information about dust-obscured star formation and hidden galactic processes within the cluster. Despite the overall suppression of star formation in the dense core, a hallmark of mature clusters, several galaxies in Abell 209's outskirts exhibit infrared excess, signaling ongoing or recent starbursts obscured in the optical and ultraviolet bands. These galaxies are often in the process of first infall into the cluster, where interactions with the intracluster medium, ICM, via ramp-pressure stripping or tidal triggering, can temporarily enhance star formation before quenching it. The spectral energy distributions, SEDs, of these dusty systems show warm dust temperatures, 30–40 K, and mid-infrared emission features consistent with polycyclic aromatic hydrocarbons, PAHs, indicating the presence of complex organic molecules and a chemically enriched interstellar medium. This challenges the notion that cluster environments are uniformly hostile to star formation, revealing a transitional population that bridges the blue star-forming field galaxies and the red, passive cluster ellipticals. Beyond the galaxies themselves, intragroup and intracluster dust, a component once thought negligible, is now being investigated through far-infrared background fluctuations and faint thermal emission. Though challenging to detect, even trace amounts of dust in the ICM could alter the thermodynamic evolution of the gas by enhancing cooling in localized regions or absorbing ultraviolet photons. Abell 209 offers a unique environment to explore this possibility, especially due to its apparent history of mergers, which could have liberated dust from galactic halos into the diffuse medium. In parallel, supernova studies within Abell 209 provide a time-resolved window into its stellar population history. Type Ia supernovae, ESNA Ia, which originate from white dwarf explosions in binary systems, act as cosmic standard candles and tracers of evolved stellar populations. Monitoring campaigns targeting Abell 209 aim to detect both hosted and hostless supernovae, those that appear in the intracluster space and likely arise from stars stripped from galaxies. The rate and spatial distribution of these explosions offer constraints on the age and distribution of the intracluster light, ICL, as well as the delay time distribution of Type Ia progenitors. Moreover, simulations and statistical models have shown that brightest cluster galaxies, BCGs, such as the one dominating the center of Abell 209, may harbor low-luminosity active galactic nuclei, AGN, that episodically inject energy into the surrounding ICM. While not as powerful as AGN outbursts in cool core clusters, these radio mode feedback events help prevent runaway cooling of the ICM and contribute to the maintenance of high-entropy cores. Subtle radio emission and X-ray cavities seen near the BCG in Abell 209 suggest a history of such activity, with implications for the cluster's thermal balance and metallicity redistribution. From a cosmological perspective, Abell 209 has been incorporated into Bayesian hierarchical modeling efforts to refine our understanding of the mass, observable scaling relations that underpin cluster cosmology. By combining lensing, X-ray, and SC measurements with a probabilistic framework, these models attempt to disentangle the scatter introduced by projection effects, asphericity, and dynamical state, factors especially relevant in partially relaxed systems like Abell 209. Accurate modeling of these relations is essential for interpreting large-scale cluster surveys and extracting robust constraints on dark energy and modified gravity. On a more abstract level, Abell 209 also factors into discussions of cosmic isotropy and statistical homogeneity. In principle, the large-scale distribution and internal dynamics of clusters across the sky should not depend on direction or location, unless a deeper anisotropy is embedded in the fabric of spacetime. Clusters like Abell 209, especially when studied in conjunction with others at similar redshift, serve as data points in cosmic variance analyses and dipole anisotropy tests, probing for potential deviations from the cosmological principle. Any such deviation, even marginal, would demand rethinking of fundamental assumptions in cosmology. Further, in attempts to detect large-scale gravitational potential perturbations, researchers have explored whether slight shifts in the cosmic microwave background (CMB) temperature can be correlated with massive structures like Abell 209, a phenomenon known as the integrated Sachs-Wolf (ISW) effect. While the signal from a single cluster is weak, stacking many such clusters, including Abell 209, enhances statistical power. Detection of the ISW effect at intermediate redshift provides a rare and direct probe of the late-time acceleration of the universe and is sensitive to the nature of dark energy. In speculative but mathematically robust frameworks, Abell 209 has also inspired models of emergent cosmic order, where the distribution of galaxies, gas, and dark matter obeys quasi-crystalline or fractal geometries in projection. Using tools like multifractal analysis, Voronoi tessellation, and persistent homology, scientists attempt to quantify whether large structures, though formed via stochastic processes, nonetheless reveal hidden symmetries or information-theoretic optimization. Abell 209, with its rich substructure, filamentary extensions, and layered galactic populations, serves as a highly structured example to test such ideas. Lastly, from the perspective of astrostatistics and big data science, Abell 209 is a training ground for new automated anomaly detection methods. By applying unsupervised clustering algorithms, topological data analysis, TDA, and explainable AI, XAI, techniques to its multispectral data cube, researchers aim to detect rare or unexpected features, such as ultradiffuse galaxies, UDGs, fossil groups, or gravitationally bound dark subhalos with minimal luminous content. These discoveries, once relegated to the periphery of cluster studies, are becoming central to understanding the completeness of our matter census. Abell 209 stands as more than a gravitational structure in deep space. It is a nexus where cosmology, particle physics, thermodynamics, information theory, and quantum speculation converge. In its web of galaxies, in its arcs of bent light, in the heat of its invisible gas, we witness the memory of the universe written across scales too vast to comprehend in a single frame of thought. It is not simply observed, it is decoded. Every filament of dark matter, every quenched galaxy drifting silently in its outskirts, every distortion of background starlight whispers of forces that shape reality itself, many of which remain unnamed. It is a relic of primordial noise, amplified into structure, and sculpted by time into an ordered system that echoes the initial fluctuations of the quantum vacuum. Through Abell 209, we glimpse the universe not as chaos, but as emergent design. Its internal turbulence and thermodynamic extremes speak to the tension between collapse and expansion, between entropy and form, between noise and signal. It reminds us that the cosmos is not still, it is evolving, calculating, self-organizing. The cluster is not just a fossil from the past but an equation still being solved, written in light, mass, and motion. In this sense, Abell 209 is a mirror, not of ourselves, but of the logic from which our universe arises. Studying it is not just an act of astronomy, it is an act of listening to the structure of reality. And in that listening, we discover that even in the silence of deep space, the universe speaks.